Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay, good afternoon, everyone. Welcome to IF Colloquium, and today is the series number 22, and today our speaker is Dr. Chakkrit Kaeonikhom. He is a lecturer in Chiang Rajabhat University, Thailand, and today he will tell us about interacting vacuum cosmology, observations, and tensions. Please welcome our speaker.
Hello, can you hear me okay? Thank you for inviting me. Hello, everyone. I am Chakkrit, and I'm going to talk about interacting vacuum cosmology in using and also using observations and to see what this model could be possible to address the tension in cosmology or not. Let me share screen. Okay, I guess you can see my screen now. It's I don't know, it's a bit weird because I don't see anyone in the room and I can't hear anyone in the room. So it's like I talk to myself on the screen. So if you not see anything, or you can.
Yes, we can see.
Yeah, okay.
We can see your screen. Thank you.
Yes. Okay, let's start. So I think people here can know a little well about the cosmological problem. It's like we will here we will talk about the an accelerating universe. In the overview, we will talk about accelerating universe and dark energy. We know that dark energy is probably a source of driving accelerating expansion of the universe. And tensions, it's tensions. We talk about tensions and interacting vacuum energy. And next I will talk about the linear scalar perturbations and the effect of interacting vacuum energy on the CMB anisotropy, and we talk about the observation like redshift-space distortion and other observations like supernova as well, and BAO, and how to use this data to constrain the model. So as we know from from the discovery of the accelerating expansion of the universe in the 1998 by two teams, and we see that the universe contains about 70% of the mysterious energy, called dark energy, and this kind of energy is driving the universe to be expanding accelerally. Do you see my cursor? I'm not sure if you could see my cursor. Right.
Sorry, I don't think I can see your cursor.
Oh. So just try to point out on the screen. Spider option. I don't know. Sorry. So yes, if you could see, maybe I can explain the picture instead. If you could see the control plot between the on the left hand side of the screen, you see the control plot that show that the dark energy is about 70% of the universe, and using observation like CMB, BAO, and supernova data. And also you can parameterize the dark energy equation of state to be like the equation of state of dark energy. It's like I didn't show here. It's like the pressure over the density, which is like the constraint in the picture in the middle show that the constraint show that the equation of state of dark energy is about -1, which is it's okay. It corresponds to cosmological constant. If you can see from Einstein equation, you have a cosmological constant term in as the second term on the left hand side of the equations above. So, but the thing is, we still have a problem like cosmological constant problem, which is the big difference between the value of cosmological constant and the vacuum energy from quantum field theory, and this kind of big difference we call that cosmological constant problem. And also in the last decade, we see that we have new problems which is called tensions. We have Hubble tension. This is you can see that in before 2014, I think, we still have the measurement of the tension. You can see on the right hand side of the screen. You can see the blue band. This is the measurement of the Hubble constant from supernova using Cepheids variable star to to calibrate the distance, and the gray band is the measurement from CMB, and we can see that if after 2014 the precision of the measurement is getting higher, and we can see that the value of the Hubble constants are mismatch. Yeah, this is it's not overlap. The value of the error is not overlap. So we call this as the Hubble tension, and this problem it's probably it's about the systematic error, or maybe there are new physics behind the there is a new physics behind this observation beyond the lambda scale model. So what I am interesting is the interacting dark energy, which is specifically we said we fix the equation of state of dark energy as -1. So, but allow the energy to exchange between dark matter and vacuum energy. We call that kind of dark energy as the vacuum energy phenomenologically. So we can see that we can fix the equation of state as -1 if we can see the constraint in this middle picture. So another tension is the called SA tension, which is the mismatch between the measurement from the Planck satellite, assuming lambda CDM model, and from the cosmic shear measurements, like from kits, you can see or DES. You can see the mismatch. Planck is here, is the gray band, gray contour in the picture, which is kind of not correspond to the other measurements in the local universe. And the SS is just defined as the sigma 8 times square root of the density parameter of the matter, and sigma 8 is the which means square. It's a kind of standard deviation of the density distribution. All right. So yes, if you have question, please interrupt me anytime. So we'll see the definition of interacting vacuum energy. This is very simple model because it's similar to the cosmological constant, but we just allow the energy density. The big V here is the can be a function of time or redshift, and the equation state of the vacuum energy is just -1. And we will see that if we use the total energy momentum tensor, sorry, this is a bit difficult because I just want to point out which equation, but I know people don't see my cursor. Let me try laser point. Okay, maybe this should work. You can see my cursor now?
Yes.
Can you? Okay, that's
Yeah.
okay. Thanks. Okay, you can see if we think about if we use the total energy momentum tensor, we can see that for matter and vacuum energy here, and they are covalently conserved. So that means these two things could be individually covalently conserved or interact with each other, right? So if we set the, oops, sorry. Can you still see my slide? Yes. Sorry, what happened? Okay, sorry. If you see this value, you can set this value as the a vector q. We call this vector q as the energy momentum transfer flow vector, and the minus sign represent the energy transfer from dark matter to vacuum energy. And if you solve this equation, we will get the equation for the vacuum energy density dot is equal to q, whereas q is just the scalar term of the energy momentum transfer factor. We can interpret q as the energy transfer, and we can see the continuity equation of the matter as well, which is the normal one. This term would be 0, but if we have interacting term, this will be some function, right? And we use dynamical analysis to try to understand the global behavior of the system. If we have interacting term in the system, we see that if we set the variable x like this, proportional to the square root of the matter density here, and y is proportional to the vacuum energy. Here we allow the vacuum energy could be positive or negative. So we found the fixed point. It's like this. If we move the fixed point, the point 3 minus or 3 plus really close. For example, if we move the 3 plus fixed point really close to the horizontal line, that means we have a small interaction. And similarly, if we move the points 3 minus to the very close to the vertical line here, we can have a small interaction as well. So if the 2 points the 2 points are on the x-axis or the y-axis, that means we have no interaction at all. And yeah, if we see the plot of the density parameter, we can see that the effect of interacting vacuum energy can change the time at the matter radiation equality. We can call radiation matter equality or whatever. Yes, if the interacting parameter here, alpha and beta, first of all, if the interacting parameter is negative, that means the matter radiation equality happen after the standard lambda CDM1. If it's positive, that means it will be this area will happen before. The gray line, you can see the gray line here, the gray dot dash line here. Let's show the lambda CDM model. And while also the color lines show the the interacting vacuum model, which is we set the value of interacting as the minus 0.2 and minus 0.2, both minus 0.2. So yeah. And after this we continue consider the in the term of linear perturbation. Firstly, we see that the vector of the energy momentum energy momentum transfer flow vector actually it can be decomposed to be the two terms, like energy transfer terms and the momentum transfer term. And yes, in this case we have we consider that the vacuum energy is undiluted. That means it's still even if the universe expands, but the density of the vacuum energy is still it's undiluted. If Q is not zero, and in Friedman's limited local work background, the energy exchange Q here depends only on time, only depends on time, which is we call that homogeneous. And the energy transfer flow vector here is we will consider that in the case of this energy transfer flow vector parallel to the dark matter flow velocity, and that means we have no momentum transfer in this case. So just only energy transfer. So we consider the linear scalar perturbation, and we write the linear perturbation as the in general form. Just consider just only scalar perturbation, and we have this metric, and A is the shift perturbation, and we have B here is a shift vector, and the C and E is the curvature perturbation, and we will have the total flow velocity of matter. It's can be written in the term of the shift perturbation and velocity, and the data here we is just defined in terms of the scale factor A, the velocity V, and the shift perturbation B. So after we set up this equation and using this metric in the for inserting in the I-star equation, we and also the energy momentum tensor, we have the solution, like, okay, if we use the conservation of energy momentum tensor, we have the energy conservation terms and the momentum equations. You see that, okay, if we have the normal matter, this term and this term will vanish, and it's a zero. And if we have the interacting term, we will have this term, and this delta V, and momentum equation as well. We will see that we have this kind of vacuum energy perturbation here happen in the momentum equations. So and also we will have the ISI constraint equation, and you can see that the momentum the vacuum energy contributes just only in in the energy constraint term, but not in the momentum constraint. So and this is kind of complicated question, and we have a model that's because this model could be reduce the complication. we call this model as the geodesic model. That means dark matter will follow the geodesics of the yeah, we follow geodesic, and the energy momentum transfer between the vacuum and dark matter will parallel to the flow vector of that. That means the three force vanishes. Right, this term is vanished for geodesic equation. And so if we set the theta c here, we call it the velocity is equal to the total velocity here. That means this term will be 0, and the three force will be 0 as well. So if we can also choose the frame that move with the dark matter. So to make it more simple, we can set the velocity of the dark matter to be 0 in a frame, right? And the vacuum energy will be homogeneous. That means the perturbation of the vacuum energy will be 0, and this make the Q the perturbation of the energy transfer will be 0 as well. We will have just only the background equation of the vacuum energy without perturbation in this frame. That will make life more easy, more easier. And also in our case, we can also set the velocity of the baryon and dark matter. It's because the energy is the velocity position of baryon and dark matter is in this case constant. We can set this so we can set the four dark matter and baryon have the same velocity potential, right? So next we can see after we solve the conservation of energy momentum tensor, we will get the continuity equation and momentum conservation equation, and we assume geodesic model, and also we assume we choose a gauge choice, which is called synchronous gauge. And if we choose synchronous gauge, sorry, I didn't write anything here. So if we choose synchronous gauge, let me go back. We will get the shift perturbation and the shift perturbation here and the lapse perturbation here. You can set to be 0. And yes, if A and B are 0, that means we will get the momentum equation. If A 0, we will get the velocity potential of the dark matter here is the rate of the velocity potential here to be will be 0, and we will get the zeta c here is a constant, which is in the synchronous gauge we can set to be 0. And yes, and the h here is just the definition of the trace of metric in synchronous gauge. And if we have interacting term, we will see this term lies in the continuity equation, but not in the momentum conservation. As just according to our assumption that we allow just only energy exchange, but no momentum transfer. So, and we can model Q. We consider simple model. I think I mentioned before that we consider this model. Yeah, this model. That's the energy exchange proportional to the matter density and plus spectrum energy density. But we can change this to be product matter. Right. So if we continue doing so, if we take the second derivative of this equation, we will get the growth equation, and we can see the interaction terms alive in the growth equation. And yeah. So we will use this equation to test the model. So we have the effect of the interacting maximum energy. We can from the observation, like CMB observation, we can see that the CMB is actually constrained a parameter that's reliable. This parameter zeta stars here for the angular acoustic scale, or you can see the angular side of the sound horizon. This is quite it's almost independent to the theoretical model, and this is very hard to break. So if we have the other theoretical model like modified gravity or early dark energy or interacting with energy, this is quite really difficult to break this constraint, because it's almost model independent. So so in the pre-analysis, we assume that the angular acoustic scale to be fixed, and then we will see what happens if we have interacting term in the model. So if we fix this, we can see the degeneracy between the Hubble parameter and the interacting model. The above picture is the we set alpha 0. We call this model as a alpha model, and we can see the Hubble parameter is the proportional to the Hubble subscript lambda. That's mean the lambda CDM model, and we have this term, right? We have this term that's proportional to the interaction parameter. And we can see this degeneracy line. This is the control plot. This value is the value of the 100 times the value of the angular acoustic scale. And for the beta model as well, in the p-analysis, the Hubble parameter is proportional to the value of beta as well. So the big F and the big J is just some function of that. Yeah. And if we see the effect on the CMB spectra, right? As we know that the effect of interacting recomposition, the time, that's mentioned the redshift at the matter radiation equality. According to this equation for the alpha model, we can see that if alpha is non-zero, so the value of that EQ, that means the matter radiation equality, will be changed. So if this error happened earlier, that means we will have the alpha will be positive, and if alpha positive, that means the energy will transfer from dark matter to vacuum energy. And if it's happened in the early time, that means the dark matter density in the early time will be less than the normal lambda CM1, and that effect will make the we make the dark matter density less than the lambda CM, and that mean we can see the shift of the whole structure of the CMB spectrum if we have less dark matter at the time. Yeah. In the pre-analysis, we know that the angular acoustic scale is really precise constrained by Planck. So if we fix this saver and also fix the physical density of the dark matter, we will see the variation of the CMB spectra narrower and smaller. That means if we use the CMB spectra to constrain the alpha parameter, we will able to see we will able to constrain the model. Yes, this is plot we use the plot from the modified Boltzmann code. We use the Boltzmann code called class. We modify this and put the parameter. If you want to see further, you can go to this link. Right. So, and for the beta model, which is that's mean alpha 0, and we can see the variation. We can notice that this value of alpha of beta is vary a lot compared to alpha. Alpha is just this one is 0.04, but in beta this is 0.4. This is 10 times, because if I value beta in to be like 0.04, that means we will not see any effect on the CMB. We see just really small change, because beta is actually affect the late universe, not the early universe. So that means we will see the really small variation on the CMB spectrum. And again, if we fix this angular acoustic scale and the physical dark matter density, we will see the variation of CMB spectra is quite fixed. That's mean the CMB spectrum cannot constrain this beta model really well. Yeah. So next we talk about the redshift-space distortion, because if we change the density field, that means this change of density field will affect the peculiar velocity of the galaxy as well, and this one, we can, this is one form continuity equation, and this term, if we use the Newtonian analysis, this term will be shown as the gradient of the peculiar velocity, and if we connect to the relativistic analysis, we will see that the peculiar velocity is just the gradient of the velocity potential in the Eulerian frame here, and if we factorize the density contrast, we will get the growth function like this. So this is the normal one. If we include the interacting vacuum energy term, we will get this extra term in the growth function, and this term could be used in the observation of F sigma h in this term, right? So we use the observation from Bose and EBOS, and we can see this is the plot of the distance. Again, we do the same thing. We did the same thing. Like we fix the present time parameter and fix the and another plot. It's we fix the theta, the angular acoustic scale, and the dark matter density at the recombination, and we will see the variation. And this shows that this data points can constrain the variation of these distances. The A is just the angular diameter distance, and BB is volume distance, and the Hubble distance from the BAO observation. And this is the beta model. Also, if we plot the growth of structure F sigma h here, we can see the variation of the parameter. Actually, the interacting parameter is quite sensitive to the growth of structure. And if we fix it to quantity, theta and omega c at recombination, we will see the change. Maybe this data point and this point could constrain the model. And for the beta model, we see if we use just only the BAO data. So we will see that the constraint, if we use just only the distances from the BAO, that means this data could not constrain really well. That's why in this work we have to use the RSD data to constrain this beta model as well, and especially the quasar data here, the green one, is how to, even if it's this theoretical prediction is not in the point, I don't know what happened, but still this is affect a lot of the in the RSD constraint, right? And yes, and observational data that we use is cosmic microwave background. We can see the variation. Yes, so we can use Planck. The TT is temperature, and TE is E mode polarization, and E is spectra to constrain this model. And also we can use the supernova data from Pantheon catalog It's called Pantheon. And we know the relation between the distance modulus and the luminosity distance, and the luminosity distance here contain the physics in the Hubble function. So if we modify the Hubble function as a new model, we can use this to constrain. We can use the supernova data to constrain the model. So, and the BAO data provide us the three quantity. If we use the RSD as well, this is the data from SSS database. So the BAO gives you the angular diameter distance over the star horizon distance at the very top, and the Hubble distance over RD and the growth of structure X. And yes, this data point is plots shown in the picture here. That's the data from SDSS. And dB is just a volume distance, is just a combination of the dA and the H. And defined in the situation. Right. So, and we use the Postman code from it's called class to and then also using the code called multi-Python, which is will give you the Markov chain multiple analysis, Markov chain multi-color analysis for the to constrain the model. And this is the we get the result here, and you can see this one is we have pre-analysis that we will see the degeneracy between the Hubble parameter and the Hubble constant and the interacting parameter alpha in this line, right? We will use Chakkrit Planck, and if we include Pantheon as well from supernova data, we can make the control plot more smaller, and also if we include BAO-RSD, we can see the value is about this, and maybe I don't show the value of alpha. But it's above 0, but it still have some big confidence level, big error. Yeah, and the value of H naught, the Hubble constant, is bigger, and this one is because we include extra parameter, that's the Hubble constant will get bigger. And this is for the alpha model, and if we see the alpha model, we can see that again the Hubble parameter is they are degeneracy between the Hubble constant and the beta, the interacting parameter. And if we use the solid Planck, we can see the bland gray contour here. We cannot constrain with the solid Planck unless we include auto model to break this degeneracy, like Pantheon catalog or BAO-RSD data. And this beta tend to be positive here. This is because of the high redshift quasar data in the BAO dataset. Sorry, this is high redshift quasar data here. Yeah. So we can plot the two model together. we will see this is the transformation from sigma to SS. We can see the lambda CDM model for the Hubble constant and SS is the green contour here, and for the alpha model is the blue one, and alpha and beta model is the red one. And we also include the combination of two models. This is called alpha and beta model, which is the gray contour. We can see the Hubble constant for the alpha model and beta model or the model here could be extended to be like about this one, and the SS. This is a bit this is another problem, because if we try to constrain, if we try to relieve the tension of the H0, we will get the tension of the SS getting worse, and vice versa. So but in the linear combination of this model, we'll see the gray contour here. It's look like this. If we try to reduce, that means getting SA to be lower, and H0 could be lower as well. Sorry, H0 could be and can make it a bit higher, but that could reduce the tension, not too much, but slightly less than 4 sigma and 2 sigma for the Hubble constant and the regressive tension SA as well. Right, if we plot the tension for the Hubble, this is compared to the other observations, but this observation is just based on lambda CDM model. But I include the interacting model in here. You can see if we use just Lee-Pang, the error just it's a bit awkward. But if we also include the Pantheon catalog supernova data and the BAO-RSD, we can see the Hubble parameter here is a bit flip up, but still not reach the blue band, which is the band of the from the choose the observation from least. Yeah, at all. Yeah, it's at all. It's from true observation. Yeah, this is my conclusion, I think. So we still have time for questions, right? Thank you.
Okay, thank you very much for the presentation. I think it is a time for questions. If you have any question, please feel free to ask.
Hi. I would like to ask a few questions. What the form of energy is used in your coupled energy model, scalar field or fluid? I'm sorry because I cannot see your slide. I ask this question first.
Oh, sorry. It's the linear combination between we have one we call alpha model, which is the energy exchange proportional to the dark matter density, and we have a couple constant times the Hubble function and the density of dark matter. And another form is the another constant times Hubble function and times the vacuum energy density.
Vacuum
And
energy density is vacuum is a cosmological constant or scalar field or something.
it's kind of a time dependent cosmological constant, similar.
Or dependent. Okay.
Yes.
So how
And
can you compute the perturbation in this quantity? Can you compute perturbation? No perturbation, right?
yeah, this one, if we choose a particular model called geodesic model, that means if we set the energy transfer follow the geodesic, that means the vacuum perturbation will automatically, no perturbation in the, at least in synchronous gauge that we choose. Yeah. So we just choose the gauge that make life easier.
Okay. Actually, I try to search for the paper that consider couple in with the time dependent vacuum energy. Okay. Because actually I am not sure how to compute perturbation in this system. Right. Yes. And in your model, the star horizon atlas scattering does not change, right?
It's a
Sound,
bit changed. And the
it's not.
sound change, but the unchanged is just the angular acoustic scale. Actually, it's changed a little bit, but we can consider as the just tiny change. We can consider as a fix in the pre-analysis.
It's changed because matter equality, deletion matter equality occur at late time compared with lambda CDM, right? Or
Yeah, it could be happen later or earlier, depends on the size of the interacting parameter.
so for this point I think about this question. If the matter relation equality occur at late time, I think the going distance to last scattering should be shorter compared with the lambda CM, right?
Yes, but just slightly.
Slightly.
Because we can't change much the acoustic angular scale, which is the ratio between the sound horizon distance and the angular diameter distance to the last scattering surface. And yeah, it could change slightly, but not too much.
Okay. Thank you.
Thank you.
Can talk later.
Okay, there is a question online from the audience online. He asks that what is the impact of including redshift-space distortions in the analysis of large-scale structure data?
So the redshift-space distortion is basically dealing with the peculiar velocity, and if the peculiar velocity change, that means the density contrast of the matter will change as well. And yes, this interacting vacuum energy could change the density contrast, because we allow energy exchange between vacuum energy and dark energy. Dark energy and vacuum energy. And yeah, so that means we'll see some effect in the velocity field as well. So yeah, so that's, I think.
Okay, thank you. If there anyone else would like to ask questions, if not, I think I think let's say thank you to our speaker, and let me end the colloquium. Thank you.
Thank you.
Okay, thank you very much.